So we're going to take a look at breadth first search, and provide kind of a brief analysis of the method. This is based on the text Artificial Intelligence by Russell and Narvik. So we had mentioned that when you're judging search algorithms, there are four components: the completeness question, optimality, then time complexity, and space complexity. So we're going to go through each of these with breadth first search. So we're assuming that the branching factor is a finite number. As far as completeness is concerned, if the shallowest goal node is at some depth d, then it will be found after all shallower non-goal nodes have been generated. So if there is a goal node, then it will be found. As far as optimality is concerned, though, the shallowest goal node is not necessarily optimal. If the path cost is based on the depth of the node and it's a non-decreasing function, then we do have optimality. And that situation does occur when all the possible actions have the same cost. But in a lot of scenarios, it doesn't have, the actions don't have the same cost. And so breadth first search is not guaranteed to be optimal. As far as time complexity is concerned, let's consider a uniform tree where each option, each node has the same number of children. So the branching factor is b, each node has b children until you get to a leaf. And so what happens, the root, generates b nodes. And so there's the root, and then there are b nodes at level 1. Each of those generates b nodes, so there are b square nodes at level 2, and this keeps going at each level, increasing the number of nodes that are there. And so the total number of nodes generated is b plus b squared all the way up to whatever b to the d, which is that nodes at level d. Now, in considering breadth first search in terms of time complexity, we're looking at the worst case scenario where the goal node is the last node at level d. So the shallowest goal is at level d, and it happens to be the last node generated at that level. All right, so we're looking at b plus b squared plus all the way up to b to the d in terms of the number of nodes generated. So how many nodes in all is that? B plus b squared all the way up to b to the d. When we add those together, we may remember that this is a geometric series, which has the form a plus a times r, and then the r is the factor that keeps being multiplied after that initial term. So to calculate the sum, we could set up the sum of s to be equal to this value that we're looking for, and then do something that I think we have seen before: multiply everything, both sides of this, by r. And so we have SR on the left-hand side, and then on the right-hand side, we've multiplied each value by r, and so we have AR all the way up to A times R to the nth power. So we can do a little algebra on this. Subtract SR from S, and on the left-hand side, we have S minus S times R. On the right-hand side, all those middle terms reduce, and we have A minus A times R to the nth power. So solving this for S, we can factor out an S from the left-hand side, and then divide both sides by 1 minus r, and then also factor out an a from the right-hand side, and have the sum is a times 1 minus r to the nth, all divided by 1 minus r. And this is assuming that r is not 1. However, if r is 1, we can still do the calculation. What do we have in that case? We have A plus A plus A plus A, and there are n of those. So when R is 1, we can still do the calculation. It's just we don't use this formula. All right, so for our scenario, where we have b plus b squared all the way up to b to the d, we notice that the first term, a, can be thought of as the b, and after that, r is also b. And so we can, in the formula, put in b for a and put in b for r and calculate that sum to know exactly how many nodes have been generated in breadth first search. All right, so for space complexity, the idea is that this method is going to store every expanded node in the explored set. And so at a particular level, big O of b to the d minus 1 nodes will have been explored, and b to the d nodes, well, big O of b to the d nodes exist in the frontier, the part that is to be explored. All right, so it turns out that in this case, space complexity is within a factor of b of the time complexity, so both of these turn out to be large in the context of breadth first search. So for an example, with just some actual numbers in place, if we have a branching factor of 10, and let's suppose that we can generate 1 million nodes per second, and that each node requires 1,000 bytes of storage. So these are reasonable kind of values, realistic kind of values for certain scenarios. And so there are some values here when we have the depth of the solution is just 2, already 110 nodes are generated. We have the root, we have 10 nodes at the first level, and then 100 nodes at the second level, so generating in all 110 nodes. So given these this situation, we're talking about finding a solution in 0.11 milliseconds and using 107 kilobytes of memory. Increase that to just a depth of 4, and we're already over 11,000 nodes and 10.6 megabytes of memory. Increasing that to 6, roughly 10 to the 6th, 1.1 seconds, and already a gigabyte. If the level of the shallowest solution is at 10, we need 10 terabytes of data, and that would take 3 hours under these conditions. If the solution, the shallowest solution, is at a level 12 or a depth of 12, it takes 13 days and a petabyte of memory. And you can see that if the depth is 16, it takes 350 years under these conditions, and the amount of memory is 10 exabytes there. All right, so what happens? This method, breadth first, doesn't work very well if you have even a branching factor as big as 10. Even if we can do what seems to us like a lot of work at each time period, it still requires a lot of time and a lot of storage to carry out breadth first completely. Okay, so what happens? In certain scenarios, the branching factor might not be as big. Eventually, you still run into the same kind of problems. Even if you have a binary tree, these numbers get big pretty quickly. And so what do we do? What we've mentioned before, you only would use breadth first in very specific scenarios, and otherwise we would continue to a different algorithm to try a different process to see if we can find our solutions much more quickly. All right, so as usual, if you have any questions, send an email, look me up on Discord. I guess you can ask questions in the comments. But otherwise, we will continue with other search methods and applying other methods for various scenarios where appropriate. Again, there are times when breadth first is perfectly appropriate and the right choice, and then there are other times where the time and space issues just become overwhelming, and so we would want to find a better method.